All right, welcome back to the online portion of today's class. So today we're going to start a new or our second data modality, which is time series. So we're going to discuss some algorithms about time series mining and how can we perform a lot of tasks on those types of signals. So before we start, I should probably um, define what's a time series. A time series is an ordered sequence of numerical observations. So we have x1, x2, all the way to xn, which is the final value of your signal. So each value is measured at a specific point in time. And often we talk about regular interval. So the main criteria of time series is that the cadence should be the same. So in case we have a cadence which is different, right? So sometimes I have minute intervals. Sometimes I have missing data, and the next I don't have data until the next hour. Then we are talking about a time sequence, not a series. So a series has a major criteria of having an equal interval between the values here. Now, the key idea behind any time series is that the order matters. So unlike tabular data, where the shuffling might not matter, shuffling the values do not matter. In other terms, I can start with feature one being the GPA, then feature two being the major, or vice versa. It won't really affect the classifier or the clustering algorithm's outcome. Here, the order between the values or the contiguity between those subsequences really matters, because we're going to see that the shape the time series makes some is relevant during the mining process. So here we see a long list of temperature-like values evolving over the time. Um, here we have three different examples of time series data from a benchmark data set, which is from the UCR benchmark data set of Keogh's group. Um, I like to give an example which are less obvious for us. For example, the last example is a pulses paradoxes problem, right? Which is typically is triggered and is shown well using the SpO2 trace, and that's what the doctors use for noticing the pulses paradoxes problems. However, it has been found that using time series mining on the ECG or the electrocardiogram data trace, which you see here on the very bottom, although on the naked eye perspective you do not see any pattern going on, but there are some microscopic patterns that if you zoom in, you should be able to see some patterns which make sense and which is also triggering of the pulses paradoxes problem. So it was very impressive to see that although normally the ACG are not used for prediction, but there has been some pattern has been found which are predictive of pulses paradoxes problems. So this is all this to say that time series mining can be sometimes very powerful at finding patterns which are not seen in on a naked eye perspective. That's on the machines and devices that the doctors might have. The second example is the middle one, and that's also a time series from nature, right? So here you could see that there is a sensor plugged on top of some insects, and they would like to see what's the insect is doing, what's the behavior of that insect while it's emitting some signal in EPG space. So here you could see that the highlighted area, or the blue highlighted area, is significant of an insect feeding behavior. So you see when the signal is idle, which is a white space here, the time series in the white background, the insect is really not eating and maybe just gazing around in the nature. But when it's feeding, it's emitting this very big perturbations that you see here, or zigzag on a zigzag fashion. in the signal here, which probably tells us that the insect is feeding. Another example is the first one here in FCC space or in the frequency domain. Again, if you just put a sensor in the nature and you're trying to see what type of birds are emitting sound in the nature, you might see that, of course, in addition to the white noise and the Gaussian noise that might exist, maybe there is a river nearby, in addition to the sound of the rain, etc. So those are typically just errors that adds up into the signal. But in addition to those, there might be the main signal that we're looking for, which is the actual sound of different birds. So in order to know what kind of bird species are around that area that we have our sensor at, we should be able to have to record what's the song the bird is emitting, and then classify what's the species of the bird. So here we could see that where there is one barbet, great barbet bird who was singing at the beginning, but starting from the second highlighted portion of the signal, there was another bird of the same species, a great barbet species, who started singing as well. So this is quite powerful as well to do some post hoc mining on the signals to try to flag what that signal means yeah, in the nature or after recording the bird singing. So time series are ubiquitous, meaning that as long as people are measuring things and things change over time, whenever we have changes and the change matter, then the time series appears. So some classical example includes blood pressure over time, presidential approvals ratings, the annual rainfall in some places, stock prices. Of course, that's the most vanilla and traditional time series data that we use. Everybody wants to predict what's the stock tomorrow in order to know whether to sell or to keep the stock in their portfolio. So it had been used across different domains, and they have more or less the same mathematical structure overall. Here you could see that in some of our research in our lab, we've been using time series for forecasting the weather in space. We also, for example, if a solar flare would happen tomorrow or not, based on the historical signal of or of magnitude of the values of the flux. We've also used time series of stream flow in order to know what's the stream flow in the Colorado, Upper Colorado region. So based on historical stream flow in different points on the map, we should be able to use it to predict what's the next stream flow in the next month, right? And in addition to that, we might also use other climate variables such as the temperature, the snow flow equivalents, etc., and make even a multivariate time series in the sense that in addition to the stream flow, I am also at the same time capturing information about what's the weather and what's the soil moisture and other variables, which makes a matrix, right? And every single point or every single multi-dimensional point in my matrix simply measures what is the weather during that time, and what is the soil moisture of at that time, and what is also the stream flow during that time as well. Okay, so this is one of the examples here of an image, and in fact, there has been a study that was published that says that if you take the image of any object, right, you can transform it into a time series, and that's kind of like the signature or kind of like the fingerprint, if you wish, of that image. It's something which characterizes that object in a unique fashion. So here, typically, you would like if you have an image, right? And I'm interested to find what's the signature of any two dimensional object in that particular image here. So So typically what do I do is that I take any point, we call it the reference point in the Euclidean space. And for every single point coordinates which outlines the object of interest over here. So let's say that my outlining algorithm has found the shape of this particular face of this person over here, and I'm interested to find the shape signature. So I take any point in my 2D space, right? And I find the rate, and I just link this point with all the point coordinates of that particular of this particular object, right? So now I'll have these are called radii, right? So, or radius, different radius, radius 1, radius 2, radius 3 over here, all the way to the final point, which I have again over here after outlining all the object point coordinates over here, which all the way to a radius n. So these different radii might have different distances, and right. So in this case, if you just plot the radius the diameter or length over here in the y-axis, right? So this is the radius, and on the x-axis, this is just the index of the point, which are the outline coordinates of my object over here. You'll get something which is known as the shape signature of that particular object. In fact, shape signature can be something which is uniquely identifying any object in the 2D or the 3D space. So this is kind of a very powerful mechanism in order to kind of recognize the objects based only and solely on their signal producing time series here. In addition to that, you can also add something which is known as the angle in between those radii. I'm not going to go into more details about it, but if you add the angle in addition to the radius distance between any point reference point and the point coordinates outlining that object, then you have a unique representation of that object, right? So meaning that this is kind of like the fingerprint of that object over here. Typically, people use the centroid of the object as being the reference point, right? So that the radii distances are kind of like not very long, or very the length is not very high from one point to another, because the centroid is kind of like on the average of the weight of that the particular 2D artifact that we're trying to find to embed as a time series. Okay, our next example here is from my work. I'm not going into so much detail over here, but the idea is that here in our in the problem that we've been handed is that we wanted to predict what's the shape of some spatial temporal sort of events at times when there was no detections recorded. In other terms, if you look at the polygons here on the right hand side, you see that I have 4 polygons, and in between I would like hopefully to find what's the shape of this first polygon that made it look like that moved from the first into the second polygon. In other terms, what is the shape morphology of the in between polygons between polygon A and polygon B at time 1 and time 3 over here? So at time 2, what is the most likely shape of the polygon which made it transform from this shape into the second shape over here? So this problem is known as a shape interpolation. And shape interpolation is nothing but kind of like an extrapolation and trying to find what is the most likely 2D morphology of the polygon moving from point time 1 to time 3 here. So I've been also using the shape signature, just like I showed in the previous slide over here, by essentially opening up this shape into a 1D, right? So a point coordinate index versus the distance from the centroid by finding the shape signature of polygon A and the polygon B from time 1 and time 3, and all the points that are in between over here using some some technique known as dynamic time warping, which we're going to talk about it in more details later on. If I just interpolate in between these 2 points and find and kind of like just have a string here between the blue signal and the green signal that I have on the bottom, I should be able to find what's the shape in between these two. In other terms, the dark blue polygons that I have here are the interpolated polygons, which looks like P0 and P2 here. So P1 prime is the most likely shape that made polygon P0 move into polygon 2 in this case. You don't have to understand this example very well, but this is just a direct application and showing you how time series can help solve some really important problems from science, which is shape interpolation. Equally important, yeah, so text as a time series. I don't know if you've heard that before, but word frequencies over text order can also be considered as a time series. This is an example from the Bible books. So here the x-axis is essentially just the dictionary of all the words that appeared in the Bible. And the y-axis is the word frequencies of those words. So the text in this case becomes a temporal signal. So the red signal is the text in Spanish versus the blue signal here is the same text of the same Bible, but when it is translated from English into Spanish here, so the English time series is the equivalent signal, but in the English text here. So you could see that there is almost a perfect match between the English and the Spanish time series, although there is some kind of discrepancies over here that you might see in between the two. But we can for sure say that we're talking about the same exact text because their distance is quite very small if you take the pairwise distance between the two signals over here. You might also use this approach of dictionary of just making a dictionary of words and frequencies of all the words that exist in two different books in different languages in order to see whether the translation has been made in a good in a good fashion, right? So good translation, of course, I'm not talking about the semantics, but just by the frequency of the words, is the one which has a more or less similar dictionary of the two books in two different languages. This is another example from the video domain. So video as time series, interesting. A video is a sequence of frames, right? And each frame has a feature vector. So we can make a time series or a multivariate time series out of different vectors which are defining objects inside of the frame. So in this example here, we wanted it's from a video of a girl in the lab who is just in the first video. Then you can see we have here about 4 frames that have been decomposed from the video. So the first one, she's wearing a red glove and she's having her hand resting and she's pointing at the end of the process towards the target. And pointing, as we might know, is just a very a normal behavior, right? So nothing scary about it or nothing insecure. In the second example, on the other hand, on the bottom of the slide, you could see the same, more or less the same behavior, but here she's pointing with a gun. She's not pointing with her fingers. So if you were just to draw the time series, if you just follow the red gloves, here, which is the object of interest from one frame to another, and just draw what's the magnitude value of the red glove as you're moving across the y-axis here. So as she moves from resting all the way to steady pointing, which is the last frame behavior here, you could see that the time series of a pointing is something that looks like this shape over here, which is shown in the red, green, and purple. On the other hand, we're having a slightly different time series, which describes the gun drawing behavior here. It's almost the same shape with the exception that we have here a hand moving to the shoulder level before she points the gun up, right? So we have a small bump before the steady pointing is going on at the end of the process. So this small bump over here is probably triggering a triggering behavior of a possible gun that is being drawn from this particular frame. So super interesting if you're interested to look at video CCTV cameras and possibly have an automatic object detection here and just in addition to the complementary data of the time series movement of that object, you could of course flag for sure a particular object as something which is potentially harmful in the frames of your cameras. Okay, another example over here, which is probably the last example, and this is handwriting, right? So handwriting can be also thought of time series or the handwriting strokes over the time. So in this case, it is used. Of course, you might think about multiple use cases, but mostly used for signature verification. It can also be used also, of course, for writer identification, right? So because everybody has a more or less unique handwriting in this case. So a George Washington manuscript has been used in this example, and we wanted to know how does the handwriting of that of George Washington looks like in terms of signal. So if you just outline as an envelope the words that the George Washington has written from the upper bound and the lower bound of his handwriting words, you should be able to have two different signals, and we call that an envelope, right? So next time someone writes those words, we can compare the envelope of the time series of the red and the blue in order to compare the handwriting. If it's more or less an exact match with some epsilon values of error, with a margin of error, of course, we can say that, hey, we're talking about the same person writing this text over here. But of course, the idea is that we already have these envelope values in our database. And next time another individual is writing a particular manuscript, we can compare it to the reference database envelope values that we have. Okay, so the next slide is about time series similarity search, and I should probably start by saying that in case if you know how to compare two time series, then you most likely know how you should be able to run most of the algorithms around the mining process of this data modality of time series. So similarity search, as you know, is very important in data mining in general. Nearest neighbor search is one of the most important one also for the vector data set. And finding similarity, if you know the similarity between objects, of course, you can cluster them, you can classify them using k-nearest neighbors. The different other methods, also density-based clustering, also are reliant on this notion of similarity here. So typically we have multiple questions that are around this concept of similarity. We would like to find a stock behaving like Facebook, or another task is how can we find similar inflation periods, find similar sales trajectories of two different items that we have in our store. So with that being said, we need to learn about what are some similarity measures which we can perform on the time series data. Okay, so we can categorize the similarities in two main categories. The first one is similarity at the level of the shape, and the second one is similarity as a structural level. So the first one, we're focusing on the row signal shape, and we're just trying to cluster them together, and we can say that, well, the two time series are looking to get similar in case they do have the same patterns, same exact pattern. Here we could see that there is a triangle shape here of a peak going on between the green time series and the blue time series, and therefore we said that they are similar. So just by the notion of their shape. Here, on the other hand, we could see that there is some other pattern which is not triangular pattern. In other terms, it's not. It is a more aggressive peak that is going on versus the first peak, which takes effect across a longer period of time for the first category of green and blue time series, and therefore the red signal is categorized as a difference category, and we can assume that this red signal is kind of dissimilar to the first cluster of time series here. So similarity at the level of the shape is totally based on a pairwise similarity between the time series and their values within the same exact times, right? So I'm looking at the general shape of the time series, and it should look something similar on average. Similarity at the structural level, on the other hand, it focuses on other notions. And when I say the structure, I should probably start by defining what is a structure. So what I mean by structure is number one, the trend, right? The second thing is the seasonality, meaning that if there is a pattern that happens every season in time, then we should see something, a pattern which is happening also on the other time series every season of time. It does not have to be exactly the same pattern, but there should be a seasonal component of the other time series in case we're talking about a structural similarity levels kind of search. And finally, the component, right? So other components are probably the cyclicity in the time series, or sometimes they're calling it cyclic error components in the time series. So here, on the other hand, you could see that the two time series, although they don't look the same, right? Shape wise, they don't look the same, because if you look at this pattern of the bump here, the V looking pattern of in the brown time series, we do not look, it doesn't look like this component exists in the green time series here. Well, there is some V, but the V here is more like is having a higher component at the end of the process with a very high magnitude at the end of the V here. So it's not the exact pattern, but what matters in the structural level is that, well, the green and the brown time series, they are both seasonal, meaning that, well, there is the V for, there is some kind of pattern, which is looking like a V for the brown. There is some time passing of a more or less steady signal. And then the pattern is happening again. So, and this with the equal cadence, right? So here from one V to another one to the other V, if you look at the delta T between the first V and the second V, it's almost the same cadence in time over here. And the same thing can be said about the green time series. Between their first pattern and the second pattern, the first delta T and the second delta T here, there is an equal cadence in time that has been passing here. So if I were just to draw the delta T's over here, so the pink segments length that I am drawing on the slide are equal in terms of length. And therefore, we're talking probably about some cyclic components. Same thing can be said about the brown signal over here. These delta t's, or the time that passed between this first pattern and the second pattern and the third pattern and the fourth pattern, is almost the same. So therefore, we categorize both signals are as similar in the case for structural level similarity. The blue signal, on the other hand, does not look like it has any kind of seasonality components, and therefore it is being clustered as its own cluster, which is quite dissimilar compared to the first cluster that we have over here. Okay, so now moving on to really more interesting stuff over here. And how can we read a signal? So any time series that you have can be decomposed into multiple components. And typically we talk about 4 components, but here people like to combine the trend and the cyclicity into one component, and they call it the cyclic trend. And therefore you're seeing only 3 components in the slides. So any time series can be decomposed into, the first thing is a seasonality. And the second thing is some error, which is just some epsilon small variation that are being added in the signal. In case the signal have been measured using by a natural phenomena or a natural process, you will always have some kind of Gaussian noise in the signal, which is, as I said in the previous example, could be just the sound on the river nearby, or the nature, or maybe the rain, as I am measuring, let's say, the great barbet bird frequency signal that it is emitting as they are singing. So seasonality is the first component, some error is the second component. The trend, of course, is one of the most important components, and the cyclicity, which we will talk about in the next slide. All right, so let's start to define, we'll start by defining each component at once. So a seasonality is a regular repeating pattern where the delta t between one pattern to another one is equal in terms of time. In other terms, here the first pattern starts and ends using in this unit of time. The second pattern happens again between in this small unit of time, etc. And if I were to draw them and just find how long is the first time unit versus the second time unit, and the third and the fourth one, or the delta t's over here, they should be equal in terms of time. So in case we have an equality in terms of the time when the patterns are repeating, then we're talking about a seasonality component here. Trend, let's start by trend. So a trend is a long-term direction of the signal, right? So it could be a positive trend or a negative trend, or sometimes here we have a clear trend going on. The trend can also be small and steady growth here with a small slope over here, right? Doesn't have to be so sharp like we have in this example over here. But the trend is something which starts at the t0 all the way to tn. We should see that overall, in general, our time series has a tendency to grow in terms, meaning that if you take a sliding window averaging, moving from the very first start of the time series all the way to the end, you should be able to see that, well, it is more or less growing in time, right? So the values are improving or having more magnitudes as the time progresses. So cyclicity, on the other hand, is the same exact after seasonality. However, the idea is that here we're talking about irregular periodic behavior. In other terms, if I were to draw a cycle here, it could be something that looks like this, right? So I have a cyclic component here. Sometimes it takes 3 units of time, sometimes it takes 10 units of time, sometimes it takes 4 units of time, right, in the x component over here. So let's say 10, sometimes here it lasted about 10 years. The first time it lasted about 3 years. The second time it happened across 4 years. Well, in this time it happened across 1 year, right? This is the pattern that I'm looking for, which is a half circle pattern. It could be any other pattern. It could be like a triangle shaped pattern, or any pattern which looks like a fluctuation which is repeating on time. But the idea is that we're talking about in terms of years between the cycles. So when you think about cycle, I want you to remember the wartime. I want you for the war happens across decades, right? So sometimes it takes 10 years, sometimes it takes 5 years to have a new war. I want you to think about the economic so the economy here, so it crashes every now and then. It's not something which is very frequent, but when it happens, it takes a long time between one economy crash to another one. So cyclicity is in terms of years. So the next slide tells us about some examples over here. And I want you to take a minute to think about what are we thinking about here in terms of cyclicity or seasonality. So is the first signal A, is it cyclic or seasonal? And the same thing about signal B. So if you were to pause the video, think about it a little bit, and then restart it to discuss what the solution in the next frame. Okay, so if you've taken some time, you must have been thinking that the first signal is definitely a seasonal signal over here. And this is because the pattern of increase and decrease over here is happening every year. So every first month of the year, which is January, we have an increased pattern and then a steady search over the Google, a search engine over here. Again, every year we have an increase and decrease. It's not exactly the same in terms of magnitude, but the shape is exactly the same one, right? So we have this kind of U-shaped increase followed by a steady shape over here. And the delta T is exactly the same here. So every year, every start of the year and every end of the year ends exactly the same way. So because the delta T is the same, we're talking about a seasonality, a seasonal component happening in my first time series. Okay, now if you were to do the same thing for the second one, right? So we have this kind of pattern going on in the second time series where we have this rectangular shape over here. So sometimes it is the stock price here in a few days, right? So in few days we have about this signal, this pattern going on and the second pattern going on. Because we're talking about it in terms of days, we cannot talk about cyclicity, right? So this is not a cyclic time series over here. We can simply say that we just have some repeating pattern in our daily stock price. Right, cyclicity, as I said, you should be very careful about the unit of time that we are using over here. So this is not cyclic nor seasonal in our case, right? So it is definitely not cyclic because it's within one day we cannot talk about cyclicity components. Okay, another example over here. So feel free to pause the video and think about it at ease. But I'm just going to skip through and discuss the solution over here. So here we're definitely talking about some trend, right? So if you look at the values, they have a tendency to increase. If you just look at the peaks that have been highlighted of the sales of the ice cream every single quarter of the year. So if you look at the peaks, seasonal peaks over here, they have a tendency to go higher. Their magnitude is getting more and more higher, meaning that overall, our sale of ice cream, regardless of the quarters, have a tendency to increase across the years. And seasonality is also happening because every single beginning of the quarter, we have a peak going on, right? So seasonal component is definitely a repeated pattern, and every quarter is what we're is our unit over here. We don't talk about any cyclicity, and of course here we're talking only about few quarters and probably few number of years. So in order to talk about cyclicity, it should be in terms of years of worth of time series data, and there is no repeated pattern across all these years. So definitely no cyclicity. Okay, so the second example, it looks like more or less steady. Although some people might think that there might be some a little bit of trend going on, but I would say that it looks like a steady signal here. So there is no trend. We can talk about some seasonality component, right? So I'll just draw the seasonality. I don't know if you agree with me, but let me just explain it to you. So seasonality is from these ups and downs and these triangular triangle-like patterns that are happening every single year of sales of this one family household of USA, right? So there is some triangle pattern up and down, and the pattern is nothing but this triangle over here. If you look at the delta T from one triangle to another one, this pattern happens every year, right? Just like the ice cream sales per quarter, it's every year. So the delta T is over here, or the length of my of my segments over here that I drew are more or less the same. So therefore, seasonality is definitely present in this signal over here. So now what about the cyclicity? I would argue that definitely this time series has a cyclicity, right? And this is based on the seasonality components are living inside of the cyclic component here. So if you were just to look at this cycle, the first cycle, the second cycle, and the third cycle component, which is not finished over here, if you like, and you see what is the delta t on the time series that you have over here from one cycle to another. So the delta t is not the same, right? The first cycle took way shorter than the second cycle. And we're talking about in terms of years, right? So the first cycle took at least more than 2 years in terms of time. The second cycle also took way more years to happen in between these different years. So definitely we're talking about a cyclic component, which I showed here as a pattern that I am drawing on the slide. So this is my first cyclic component. And within the cyclic component, we have a seasonal component that lives inside of it. Which is this triangle shape that is taking effect inside every single cycle. So we are able to talk about cycle because the unit of time here allows us to do so. So definitely we have a repeating pattern with irregular intervals, and in terms of at least 2 years that is in which the pattern is taking place. So therefore we're talking about a cyclic and a seasonal time series without any trend component in this slide. Okay, so two kinds of similarities, just like I talked about previously. So two kinds of similarity. The first one are shape-based, like I showed at the very beginning, where we're talking about the actual shape of the time series. So here, shape-based similarity. In order to find this kind of similarities, typically we rely on methods such as the LP norms, also known as Euclidean distance or the L1 norm, which is also known as the Manhattan distance. So typically those types of methods finds the pairwise distances between every single point and its corresponding point on the other time series and aggregate them across the whole length of the time series, meaning that I will find the distance between the point coordinates at time 0 and the first point coordinates at time 0 of time series 1, then time series 2. I'll find what is the distance between the second point of my green time series and the blue time series over here. And if you take the aggregate or the sum of all those distances over here, that tells me, hey, what is my LP norm in terms of either Euclidean distance or L1 norm, which is the Manhattan distance. So we're going to talk about those in a second here. On the other hand, we have the non-Euclidean or structural level similarities. So structural level similarities do not really concentrate on a pairwise the pairwise search or a pairwise distance aggregation between one point to another one, because as I said, it is looking at the components of the time series, not really the shape of the time series from one point to another here. So structural similarity search includes methods that relies on some kind of representation learning of the time series, right? So if you would like, some methods are, for example, the longest common subsequence is an example of similarity search at the structural level here. So dynamic time warping is another method from the shape-based similarity. It's known as as an elastic method, which is a little bit more expensive than the LP norms, but it is way more efficient. So because it's also relying on how the shape of the two signals looks like, it is also categorized in the shape-based similarity. Okay, so now we're moving on to the definitions, and here I'm going to show you what's the difference between a distance measure and a distance metric. So you might notice that in the data mining community, some people might use them interchangeably, and that's a big red flag. And in fact, it is an error from our end as data miners to do so. So a measure is definitely way lower in terms of rank than a metric. A metric is something which is very powerful. In fact, if we're talking about a metric, a distance metric, it simply means that if we have a metric, then we have the ability to index our data set based on that particular distance metric, right? A measure does not allow us to do so directly unless it has the property of triangular inequality. So if we have two objects, O1 and O2, in this case, the object could be a time series over here. The distance is denoted using the D of O1 and O2, or TS1 and TS2 in case of time series over here. So this is just a definition of distance over here. Of course, we say that the higher the distance, the lower the similarity, and the lower the distance, the higher the similarity. Therefore, we say that the distance measure is a measure of dissimilarity between objects or between time series. So, in fact, there are many desirable properties that a that any distance measure might have or might not. But ideally, a distance metric has all these four properties. If any distance measure satisfies these four properties, then we say that this measure is in fact a metric, and it is very powerful. We can use it for indexing. So the four different properties are as follows. The first one is symmetry, which means that the distance between A and B is equal to distance B to A. The non-negativity, so ideally we would like the distance to always be positive, otherwise negative. Of course, you might think about problems with this measure, because if I would like to aggregate distances together while one distance is negative and another one is positive, then it is not really a true reflection of the similarities between by adding those distances together, right? So because I am aggregating distances, I don't want the distance to be negative at any point. The third one is the identity, and finally the triangular inequality. I'm going to zoom in each one of these properties in the next slides. Okay. First one is similarity, and that means the distance between time series 1 and time series B must be equal to the distance between time series B and time series A, right? So here, the order does not matter whether I chose a distance between A and B or B on A. So who can think about an example where a measure does not satisfy the symmetry property? Okay, so an example of that is the Kullback or KL measure, right? So here in case you would like to, the Kullback-Leibler divergence is always a non-negative real number between 0 and 1. But if you start by finding the distance between one histogram to another one, so KL divergence distance might be different than if you start from the second histogram and to the first one. In other terms, if you just call the function to find the Kullback-Leibler divergence between histogram A and histogram B, it will give you a different number than if you would call the same exact function by starting from histogram B, then histogram A as the input input parameter of that particular function. So symmetry is not a criteria, is not a property which is satisfied by the Kullback-Leibler divergence measure here. Okay, so symmetry is very important. Most of the distance measures satisfy it, but as I said, there are some other measures which don't, just like the KL divergence here, which is not for time series, is for histograms. The second one is the non-negativity. As I said, we want our distances to be greater or equal than 0, so no negative distances, meaning that the distance between any time series should be strictly positive in this case. The identity property, super important as well, and it says that the distance between two objects should be 0 if and only if the distance is between the object and itself. right? So there should not be a distance of 0 between any two different objects which do not have the exact same values in their time series, right? So, and this is known as the identity property of a distance measure. The final one, which is kind of like the hard one, and it's hard to satisfy as well from distance measures perspective, but it is one of the main criteria which makes the distance measure a metric. And this is known as the triangular inequality. So a triangular inequality simply says that if I know the distance between an object A and B, then this particular distance must be less or equal to the distance to A to C plus the distance between B to C. In other terms, if I just include one time series in between A and B over here, which is C, then the sum of those two distances must be greater or equal than A to B. And that kind of like should ring a bell and remind you of the triangle property that you've seen in math, right? So, which is the distance between the distance or not the distance in this case, the length of one side of the triangle must be less or equal than the sum of the two sides of the triangle, right? So, and that's kind of like a property which also holds for the case of distances between time series in case that measure satisfies the inequality this property over here. It's one of the hardest to achieve though. So why is this important? I'm going to show you an example of why the inequality property is very important in this case. So suppose I'm looking for a database of objects. So we have so let's just say that I projected my time series A, B, and C, which are my 3 points over here in 2D. Maybe I use something like dimensionality reductions, like PCA, which we've seen in the earlier in class over here. And because I have a database which is already stored in my server, I already pre-calculated this distance matrix here, which is essentially the distance between A and B, and C, and the distance between B and C. You might see that here the half of the matrix is sparse, and that's simply because those values are repeated, right? So we only care about one triangle in this case. So since I already computed the distance between A and C, the distance between A and C is also reflected on the last cell of my matrix. So I don't need to I don't need to fill in the matrix twice with the same number over here. Well, the same thing is happening for the diagonal. The diagonal is sparse because simply the distance between two objects which are similar are equal to 0 in case we're talking about a distance measure which satisfies the identity property over here. Okay, so let's just say that I have this matrix in hand, and that's because the data set that I have that I have in my server, I already pre-computed these values. Now let's say that I have a query point or a new time series at runtime in my operational model wants to find what's my nearest neighbor, one nearest neighbor here. So my query point here can I can start by finding what's the distance between my query point and the first and one of the time series, which is A, and I found that, well, there are 2 units apart from each other, right? So Q and A are only 2 units apart from each other. Now I can also find the distance between my other point which I have in the database, which is Q and B, right? And I have found that they're about 7.8 units from each other if I just compute the distance between Q and A and Q and B. So 2 units from A and 7.8 units from B. Now, because I already have these two informations, I don't really need to compute Q and C because maybe my distance measure takes a long time. If my distance measure satisfies the triangular inequality, I do know for sure that the distance between Q and B is less or equal than Q and C and plus the distance between B and C, which I already have. right? So the distance between B and C, already have that from my pre-computed table over here. I just need to plug it in the case of B and C. I already know what's the distance between Q and B, which I computed over here, and I can deduce what's the distance between Q and C thanks to this inequality over here. And I do know for sure that the distance between Q and C should be greater or equal than 7.8 minus 2.3, which I have in my pre-computed table, which is greater than 5.51. And with that being said, because I already know that thanks to my triangular inequality, that the distance between Q and C, which I don't know because I did not compute, I already know that it's greater or equal to 5.51. Because I know this, I don't even know, I don't even need to compute the actual value, because I already know that one of my nearest neighbors is 2 units apart from myself, which is the distance between Q and A. So that's the winner point over here. So this is my one nearest neighbor over here. And that way, I really took a shortcut from computing all the distances between the query point and all the points that I have in my database. Instead of that, I just used some deductions, which is the shortcut here, in order to in order to not compute some distances because they were not necessary for me in this case. Okay, so this is kind of the reason why we might want to choose a distance measure which satisfies the triangular inequality. And more importantly than this, a measure which satisfies the triangular inequality allows me to do indexing, because indexing, the big idea behind indexing is that I will follow part of the search, and kind of like ignore some parts of the search, because I know for sure that it does not apply the distance is greater than some areas of my search space thanks to the triangular inequality, right? So if you think about, let's say, a B tree indexing in your data structure, you go left or right in the tree, and by default you're just ignoring the other side of the tree. If you're taking right, then you ignore all the left forever, because I know that my search is for sure in the right hand side of my tree. So that way, I know that thanks to the triangular inequality, I can rely on these kinds of shortcuts for indexing my database. Okay, so distance measures we have, as I said earlier, for the case of a shape-based similarity, I could use Euclidean measures. There are also non-Euclidean measures that are typically used for the structural similarity search. So Euclidean simply means that I'm relying on the values in the exact point of time in which they happen. Non-Euclidean simply means that I am relying non-Euclidean distance is simply based on the properties of some points, but not at their exact location in space. An example of non-Euclidean measure is the longest common subsequence, right? I would like to find if a sequence, if these two signals, the red and the blue, share a pattern, but I don't care where they happen, right? I just care whether the pattern happens in the two time series, right? So this is an example of a non-Euclidean. Euclidean, on the other hand, means that I want to know whether they have the same exact patterns at the same exact time, right? And that's what Euclidean restriction means have in this case. The first example of Euclidean is the L2 norm, also known as the Euclidean measure, and it's nothing but the square root of the sum of the difference between the 2 points as the 2 points of the time series Q and C that I'm trying to find the distance between squared in this case. In other terms, if I just go 1 point to another one over here between Q and C, and of course they all live within their y magnitude x over here, right? So if you just take the distance between what's the value here and what's the value of Q here, one by one, right? And you keep going all the way to the end of the two time series here. I'm having all the way to n, right? So starting from index 0 to n, Again, starting from index 0 all the way to index n, which is the last point of my time series. If I just take, okay, let's say here I have value of 4 and here value of 3, right? I'll just take the distance between Q and C in terms of Euclidean distance is nothing but 4 minus 3 squared plus the second point here is, let's say it is about 3.9, right? And the second point in my second time series here is about 2.5, right? Plus 3.9, right? Minus 2.5 here squared, etc., until I finish all the point that I have. And if you take the square root of all this aggregation, then this is my Euclidean or L2 norm, Euclidean distance between the two time series Q and C. In this case, most of the works that have been published, they use Euclidean distance as their basic basis for finding similarities between time series. Okay, so this is just an example for you to compute what's the time series, what is the Euclidean distance between these two time series. So if you do the math here, it should be around 6.86. I've already pre-computed this for you, but the idea is here is that if you just follow the same formula that you have in the previous slide, which is essentially Qi minus let's call it here I, right? Ti, and you take here the square root squared, and the sum aggregation from I is equal to 1 equals to 1 all the way to n here. So you should see that n here is equal to 5, right? Because that's the end the last index over here, and that's the formula that we have on the slide on the top in this case. So the distance, if you were to do that, then this is nothing but 5 minus 1, 4, 4 square, plus 4 minus 2, 2 square, right? 3 minus 2, which is 1, 1 square over here, plus 1 square, another 1 square, because it's exactly the same value, right? Here we have 4 minus 1, which is 3 square, and 5 minus 1 again, which is 4 square. So if you add all these values that I just computed here, and you take the square root over them, that's the distance over here. So 4 square plus 2 square plus 1 square plus 1 square plus 3 square plus 4 square over here is equal to 47, right? If you take the square root of 47, that should give you the value of your distance over here, which is essentially equals to 6.8. Around 6.8 is the value of your distance measure or Euclidean distance between these two time series. Okay, optimizing the Euclidean distance. Some, if you would like, and this is a minor change that you could do. Of course, you might see that because here we already squares, we already take the square of the difference between the two time series indices at different times. It's already a positive values that we're aggregating using the sum, so you can easily remove the square root over here. That can allow you to have some additional time savings by not taking the square root over here. It's kind of minor, but it's something to be aware of. So square root here does not matter for us for the sake of similarity search of time series. So the second one is an L1 norm, and that's the last measure that we're going to talk about today. It's also Euclidean distance, because it's finding the pairwise distance between the two signals Q and C over here. So the distance using L1 norm is also known as a Manhattan distance, and now we are using the absolute value, the aggregate of the absolute value between Q and C, as we're moving from one index 1 all the way to the index n over here. It goes as follows, right? So now instead of taking the square root of the aggregate square differences over here, I'm just taking, well, 4, the absolute value of 4 plus 2 plus 1 plus 1 plus 3 plus 4, which is equal to 15 in this case. Manhattan distance is also similar to Euclidean distance, although if you plug either L1 or L2 to different algorithms, they might give you different results. In fact, using one distance with the k nearest neighbor or another distance with the k nearest neighbor is considered to be a hyperparameter. So different, they behave differently. So let's say Manhattan distance might be good for the electrocardiogram data, k nearest neighbor search, while the Euclidean distance might be better for the case of the Great Barbet classification example that we've seen at the beginning of the class, right? So distance, choosing the right distance for your algorithm is a hyperparameter of your algorithm that we have. Okay, so I think that's the last slide that I would like to stop at over here. So today we learned about what a time series is, what type of similarities can be done on the time series, and what's the properties which makes one distance one distance metric way more powerful than the distance measures over here. I will let you work on the handout, and please bring your questions to class in the next class. I'll see you soon. Thank you.